Alright guys, now I'm going to teach you how carbonyl compounds react, beginning with a short analogy. I want you to imagine a happy man who happens to be a stick figure standing in this kind of posture. Now if this man gets hit in the groin with a football at high speed, the product formed from that reaction will be this. Carbonyl compounds react in much the same way. If you can imagine a carbonyl compound, as shown here, being kind of like my stick figure man, you can see that this carbon represents his groin, and this R and Y groups are his legs, and this is his torso. You can imagine a football coming into his crotch, just as we showed before. Instead of a football, however, this is going to be a nucleophile, represented here by Z-. When Z- comes in to this carbon atom, however, it can react or respond a little bit differently from the way that the man responded when a football hit him. When he got hit by a football, there was only one response he could have, and that was to go down. When a carbonyl compound gets hit by a nucleophile Z-, it can respond by having these pi electrons go up onto the oxygen. Thus, Z- comes into this carbon, and these pi electrons go up onto this oxygen, giving this tetrahedral intermediate, where there's an O- here. When this minus charge on the oxygen collapses back down to reform this double bond, closing like a trap door, it kicks off Y- as a leaving group, giving this kind of product shown here. Now I have to warn you that Y- will only get expelled if it's a better leaving group than Z-. If Z- is a better leaving group than Y-, then when the minus charge on the oxygen comes back down, it will actually kick off Z, reverting back to the starting material, instead of kicking off Y-. Now in the case of aldehydes and ketones, Y here would be a hydrogen or an alkyl group. Hydrogen and alkyl group are very, very poor leaving groups, so the O- cannot come down and kick off an H- or a carbon with a minus charge on it, because that would be extremely unstable. Hence, for aldehydes and ketones, this minus charge does not come down to reform a double bond and give this kind of product. It does something a little bit different, which we will discuss later on in Chapter 18. For all of the compounds covered in this chapter, however, we have to remember that the nucleophile comes right into the crotch of the carbonyl, kicks the pi electrons onto the oxygen, giving me this tetrahedral intermediate. Then the minus charge on the oxygen comes down, kicks off this leaving group Y, and gives me this kind of product. Now I offer you a word of warning and some counsel. The mechanisms in these reactions are extremely repetitive. In fact, from one reaction to the next, you'll see that the mechanisms are more or less identical with only minor variations. Now, if you gain the ability to see this pattern, to see the repetitive nature of these mechanisms, learning the material in this chapter will be easy. It will be as though you are only learning one or maybe just a few reactions instead of dozens. This mechanistic repetitiveness reminds me of a contemporary song that I was recently exposed to, which I found to be absolutely hilarious. It went something like this. Barbara Streisand. And then that sequence was repeated about 900 times. You should begin to see as we cover this chapter that the mechanisms here are extremely repetitive. Thus, you don't have to feel like you're learning 900 different reactions. You're really only learning just one reaction repeated about 900 different times, like the Barbara Streisand song, with only slight variations here and there. This chart rates leaving groups from best to worst. Because chloride is such a great leaving group, acid chlorides are super reactive, and they're the most reactive in the series. NH2- is a very, very bad leaving group, and that's the reason why amides are the least reactive in this series. That's actually a good thing, since proteins are made up of large chains of amide bonds. If NH2 were a good leaving group, then every time we drank water, all of the proteins in our bodies would gradually dissolve as the nitrogen or amide bond was being displaced by the oxygen from the water. Fortunately, that does not occur, and I'm grateful for it. This slide summarizes all of the reactions featured in the first half of Chapter 17. As you can see, what we'll learn is that you can start with a number of acid derivatives, and depending on what Y is, you can displace it with a hydroxide nucleophile to form a carboxylic acid, with an alcohol as a nucleophile to form an ester, with an amine like ammonia or another amine as a nucleophile to form an amide, and then Grignard reactions, which we actually won't cover until later on. With that overview now given, we're going to look at every single one of these, one at a time. Here's an acid chloride, and as you can see, when acid chloride is reacted with a methoxide nucleophile, the methoxide group replaces the chlorine to form an ester. I've also written here that if you try to do the reverse, that is, have a chloride nucleophile come in and displace the methoxide, you get no reaction. I want you to think to yourselves, why in the world is there no reaction occurring in the second case? I'll answer that in 2 slides. But first, I want to address the mechanism for the first reaction. So here's my starting material. It's an acid chloride. How in the world is that Cl displaced? Well, my methoxide nucleophile comes into this carbonyl carbon. These electrons get thrust up onto that oxygen, and it generates this tetrahedral intermediate. The negative charge on the oxygen then comes down and closes here like a trap door to form a double bond here, pushing off the chloride as a leaving group. This then gives this intermediate, or this product I should say, which is my methyl ester and chloride leaving group taking off. So I asked you earlier, why can't you do the reverse? That is, why can't I take a chloride and displace an OCH3 with it? This would be the mechanism of that reaction. If I started with my methyl ester and had my chloride nucleophile come into the carbonyl carbon, the electrons would then go up onto that oxygen, generating this tetrahedral intermediate. The O- then comes down, closes to form a double bond here, kicking off the OCH3. That would then give my theoretical acid chloride product. So I'm telling you that this reaction does not occur. Why doesn't it occur? Well, the reason is because this step is total crap. Why? Because a chloride is a better leaving group than an OCH3. Chlorine is better able to handle a negative charge. So when this negative charge comes down to close that and form a double bond, in reality it would not kick off an OCH3, it would kick off the chloride and go back to the starting material. Hence, this resolidifies the principle I taught a few slides ago. These kinds of reactions only occur when the nucleophile is not as good of a leaving group as the leaving group. If your leaving group here is actually a poorer leaving group than the nucleophile, then this reaction will not occur. Let's take a look at reactions of acid halides. Because acid chlorides are so reactive due to the stability of the chloride, and hence the chloride being a good leaving group, we can displace the chloride with lots of different things. For example, if I take a chloride or an acid chloride and I react it with an acetate, I can replace this chloride with my oxygen, giving me an acid anhydride. Similarly, I can replace the chloride with an OCH3 to form an ester under neutral conditions. Now you'll remember the previous slide I had a methoxide where there was a solid minus charge on this oxygen, but I can also do that under neutral conditions. What are the mechanisms of these reactions? Let's look at the first one. I have my acid chloride. My acetate anion comes into that carbonyl carbon, pushes the electrons up onto that oxygen, giving me this tetrahedral intermediate. The negative charge then comes down, closes like a door to form a double bond, and kicks off the chloride leaving group. This gives me my final product, which is an acid anhydride, and my chloride leaving group as a byproduct. What is the mechanism of displacing the chloride with an alcoholic group? Well, here's what I do. I have my alcohol, in this case methanol, reacting with my acid chloride. The electrons come in, they hit that carbonyl carbon, thrusting the electrons onto that oxygen and giving me a tetrahedral intermediate. I hope you're noticing how repetitive these mechanisms really are. Once I get to that tetrahedral intermediate, the electrons on the oxygen come down and kick off my chloride leaving group, giving me this temporary intermediate. To neutralize this oxygen, the chloride then comes, grabs that proton, and pushes these electrons into the oxygen. That gives me my final product, which is an ester, and hydrochloric acid as a byproduct. Hence, we can see that we can also form an ester from an acid chloride using a neutral alcohol rather than a methoxide or an alkoxide anion. Another reaction that we can do and can imagine is displacing this chloride with an OH. That can be done under neutral conditions by treating the acid chloride with water. Acid chloride, or the electrons on the water come in, electrons go up, then the electrons come down and kick off the chloride, giving me this intermediate, and then a base, which could be the chloride or it could be solvent, comes and deprotonates this to give me my carboxylic acid product. We can also convert acid chlorides into amides, that is, replacing the Cl with an NH2 using ammonia. What is the mechanism of that? Well, you'll probably see a lot of repetition here. I have my acid chloride sitting there, and my ammonia, that is the lone pairs on the nitrogen in ammonia, come into this carbonyl carbon, thrusting the electrons up onto the oxygen. This negatively charged tetrahedral intermediate sits there momentarily, and then the electrons come down and kick off my chloride leaving group. That gives me this intermediate. The chloride can then come around, deprotonate that compound, neutralizing the nitrogen's positive charge and giving me my amide, along with HCl as a byproduct. There are reactions I can do to either form or convert acid anhydrides to other products. In this example, I have sodium formate being reacted with an acid chloride to form an acid anhydride. We talked about that earlier and showed the mechanism, but I'll probably show it again. I can also convert acid anhydrides to esters by reacting them with alcohols. What are the mechanisms for these reactions? Well, naturally, I'm going to show you. In the first reaction, I've got this formate interacting with an acid chloride. Electrons on this oxygen that has a negative charge come in, thrust up onto this oxygen, giving a minus charge. This is my tetrahedral intermediate. And then those come back down and kick off my chloride leaving group. This forms a double bond and gives me my acid anhydride product and my chloride byproduct. The mechanism of the second reaction is also similar. I have an alcohol that comes in to one of these carbonyls. It doesn't matter which one because this acid anhydride is completely symmetrical. Those electrons then get thrust up onto the oxygen, giving me this tetrahedral intermediate. This O- comes back down, collapses to give a double bond, and kicks off this as my leaving group. This gives me this intermediate. Of course, I have this protonated oxygen that's positively charged and not happy. So this acetate that was my leaving group from this step deprotonates, thrusts the electrons into that oxygen to neutralize the charge, and gives me my ester product. And you'll notice that when this O- steals that proton, it also forms this carboxylic acid byproduct. This kind of reaction can be applied to acid anhydrides in numbers of different ways. If I take hydroxide, for example, and I deprotonate this phenol, the O minus, can come in here, electrons go up, electrons go down, and kick off my acetate leaving group. This forms this kind of product, which is an ester from salicylic acid. This should look familiar to those of you who have taken my lab class last semester, because we ran this reaction in the lab. We took salicylic acid and treated it with acetic anhydride to make aspirin. Another reaction that we can do is treating an acid anhydride with water to form carboxylic acid. I'm going to show the mechanism of this on the next slide. Here's my acid anhydride. I have water. The lone pairs on the oxygen come in. Once again, electrons go up, giving me this tetrahedral intermediate. Now this O minus electrons are going to come back down and kick off this acetate leaving group. That gives me this intermediate. Now you'll notice that this oxygen is positively charged and wants to be neutralized. We can have that occur by having this acetate, which is the leaving group from the previous step, come and deprotonate, thrusting these electrons into that oxygen to neutralize it. You'll notice that we make our carboxylic acid product, and when this O minus steals this proton, it also makes the exact same product again. So when we take an acid anhydride that's symmetrical at least, and hydrolyze it with water, we in reality get 2 moles, or 2 equivalents, of carboxylic acid out the other end. The remaining reactions I will not be showing mechanisms for, but they follow the exact same pattern as the mechanisms that we've shown thus far. Consequently, I can treat an acid anhydride with an amine. It can be an amine that has an alkyl group on it or not. And the electrons on the nitrogen will come into this carbon. Electrons go up, electrons go down, kick off this yellow highlighted leaving group to form an amide. Here's a neat example of that. If I take this compound, p-hydroxyaniline, the nitrogen electrons can come in and attack acetic anhydride here. Electrons go up, electrons go down, kick off this green group, and I form this compound, acetaminophen, which you guys will probably be very familiar with and have very likely taken to treat your headaches. Now I'm going to cover and address reactions of esters. As you can well imagine, if we treat an ester with water and acid, we can displace the OCH3 with an OH. I'm not going to show the mechanism for this. It is very similar to the mechanisms we've shown in the past, but this HCl acts as a catalyst to protonate oxygens and form better leaving groups than we would otherwise have. I consult you guys to look at this in your book. Once again, we can imagine the oxygen lone pairs coming in, and the electrons rearranging and then closing back down and kicking off this OCH3 as a leaving group. It gets protonated under these acidic conditions, thereby forming an alcohol as a product. This type of reaction, where I form a carboxylic acid from an ester, is called a hydrolysis reaction. I can also displace the O-alkyl group in an ester with a nitrogen, forming an amide. Reaction conditions or mechanisms very similar. Electrons on the nitrogen come in, electrons go up, electrons go down, and then kick off this ethoxy group. It steals a proton back from the nitrogen to neutralize its positive charge, thereby giving me ethanol as a byproduct. We can convert some esters into different esters as well. If I take an ester of this type and incubate it with a large amount of this alcohol and catalytic acid, the lone pairs on this alcohol oxygen will come in, electrons go up, electrons go down, and eventually displace this OCH3 as an alcohol leaving group. This is a way of converting one ester into a different ester. This kind of reaction is called a transesterification. We can also convert carboxylic acids into acid chlorides. Now this might blow your mind. Maybe by this stage you're asleep, I'm not sure. But it blows my mind initially, simply because I've taught you earlier that a chlorine is a better leaving group than an OH. Hence, you shouldn't ever be able to replace an OH with a chlorine, right? Well, as it turns out, you can do that using this reaction, or this reagent, thionyl chloride, which I like to call affectionately Socyl 2. Socyl 2 actually goes through a reaction mechanism highlighted in here to convert the OH into a better leaving group than a chloride. Hence, the chloride's able to then come up and displace that leaving group. Thus, you can take a carboxylic acid and you can convert the OH into a Cl if you treat it with Socyl 2. For this particular reaction, I am not going to require you guys to know the mechanism. I do, however, want you to know the conditions to convert a carboxylic acid into an acid chloride. And remember, those conditions are Socyl 2. I can also convert a carboxylic acid into an ester. If I take a carboxylic acid and treat it with an excess amount of alcohol and some acid catalyst, I can displace the OH for my O-alkyl group. Thus, I've converted benzoic acid here into ethyl benzoate. This type of reaction, the conversion of a carboxylic acid into an ester under these conditions, is called a Fischer esterification. A way of converting a carboxylic acid into an amide that is a little bit more efficient and easier is by incubating the carboxylic acid with this reagent called DCC. I am not going to require you guys to know the mechanism of this reaction at all. I just want you to understand that DCC does make an OH a wicked good leaving group. Thus, it makes it so that an amine can come in and kick off that OH even faster and better than it normally would. When we compare this with the amide formation covered a few slides ago, you incubate a carboxylic acid with DCC and amine, you can typically form an amide under room temperature very, very easily. If you use just an amine by itself with catalytic acid, you generally have to heat it up. So DCC is a great reagent for making an OH a better leaving group and enabling you to take a carboxylic acid and convert it into an amide. You can also convert amides back into carboxylic acids. Now, as I mentioned, an NH2 is actually a worse leaving group than an OH. So it's pretty hard to have an OH come in here and kick off an NH2. The only way that you can really do this is by treating it with an excessive amount of acid or base with water as the solvent and heating the holy crap out of it. That way you can displace the NH2 with an OH, forming a carboxylic acid and releasing ammonia as a gas. Here's a great example of this. I can take N-methylbenzamide, shown here, incubate it with ethanol, heat the snot out of it with HCl, and form this, ethyl benzoate. This is another reaction that follows a mechanism that's very different from the ones that we've shown so far. I'm not going to require you to know the mechanism for this reaction. I do, however, want you to know the conditions. I can take an amide and convert it into a nitrile by incubating it under warm conditions with P2O5, which is phosphorus pentoxide. That's a very, very cool way of forming a nitrile. With that said, I now am going to conclude by sharing a lecture problem with you guys. I want you to predict the products of each of the following nucleophilic acyl substitution reactions. I'm not going to cover the answers in this presentation for you, but I hope that you guys will at least do your best to try and figure out the answers to these questions. If you have any questions, we can talk about them later in class. So now we'll finish with a recap of all of the carbonyl reactions that we've learned so far in this chapter. First, if we take an acid chloride and treat it with water, we can hydrolyze the chlorine, replacing it with a hydroxyl group to make carboxylic acid. Analogous treatment with alcohol forms esters. treatment with ammonia or other amines can make amides, and treatment with an acetate comes in, electrons go up, down, kick off the chloride to form an acid anhydride. Similarly, we can do various reactions with acid anhydrides, which is the next most reactive carbonyl-bearing substance in the sequence. We clip off the acetate leaving group with water, we get carboxylic acids. With alcohol, we get esters. With amines, we get amides. We can also do reactions with esters, which are the next most reactive species in the sequence. We can hydrolyze off the alkoxide group with water to form carboxylic acids, with amines to form amides, and with other alcohols to form different esters. This sequence is called a transesterification catalyzed by acid. Here are the reactions of carboxylic acids. If I treat them with an alcohol, catalytic acid, I can form an ester. This process is called Fischer esterification. I can convert the hydroxyl group into chlorine using thionyl chloride or Socyl-2. And I can replace the OH with an amine group, thereby forming an amide by treatment with an amine, various amines of choice, and this reaction, DCC. I'm not going to require you to know the mechanism of that. I will only briefly say that DCC helps convert the OH into a better leaving group. Here are the reactions of amides, which are some of the least reactive species in the sequence, because an NH- is a much poorer leaving group than an O- or a Cl-. But if we heat the holy snot out of an amide using water, we can replace the NH2 with an OH, converting it into a carboxylic acid. If we treat it with this dehydrating reagent, P2O5, phosphorus pentoxide, it will convert the amide into this species, a nitrile. Or if we heat the holy snot out of the amide with an alcohol, we can form an ester from it. That brings us to the end of this section of Chapter 17, coverage of carboxylic acids and their derivatives and their reactions. I hope that you've had as wonderful and enjoyable of a time as I have. I'll see you in our next video.